Here are 5 key reasons why gears matter. The first one is speed reduction. In general, standard AC electric motors operate at relatively high speeds, so 1800 to 3600 RPM respectively, while many equipment applications such as pumps, mixers, or conveyors require much lower operating speeds. Gears reduce output speed to the optimal level for the specific application and the equipment requirement. Number 2, torque multiplication. As speed is reduced through gearing, torque increases. We'll review the quantification process of this principle and demonstrate how gearing allows small motors to drive heavy loads. Third, efficient power transfer. Gears transfer mechanical power from motors or servos to the driven equipment with high efficiency while maintaining precise motion and load control. Fourth, system matching. Moreover, gears help match motor performance to system requirements, ensuring equipment operates with optimal performance within its optimal performance ranges. And then finally, equipment protection. Proper gearing can reduce mechanical stress, absorb shock loads, and improve reliability of the overall system. Here are a few examples of some of the common gear types organized by geometry and application relevance. So to the very far left, the first set are parallel shaft gears. Examples of parallel shaft gears include the spur, helical, and double helical gears. These gear sets have either straight or angled teeth, are simplistic in nature, cost-effective, and are used as basic speed reducers for industrial equipment, pumps and compressors, turbines, and conveyors. Next are intersecting shaft gears, which consist of both bevel and spiral bevel gears. The shaft-mounted bevel gear has a cone-shaped configuration, intersects the opposing gear at a 90-degree angle, and is used primarily for changes in rotation, in right-angle gear drives, mixing equipment, automotive differentials, etc. Spiral bevel gears have curved teeth and are rated for higher load capacities and are used in heavy industrial drives. Third are non-parallel or non-intersecting shaft gears. Examples of these would include worm and hypoid gears. So for instance, worm gears have a screw-like gear and a worm wheel, and these are used primarily for high speed reductions in lifts and conveyors, and also positioning systems, while hypoid gears, designed similarly to bevel gears, minus the intersecting shaft, are used for high torque load applications such as automotive drivetrains. Planetary gears, which we'll discuss in depth throughout the course of the presentation, are also known as epicycle gears. They are used in applications such as submersible mixing, robotics, and wind turbines. Finally are the rack or the flat and the pinion round gears. They convert rotational motion into linear motion and are used in equipment such as valve actuators, and steering systems. Now we'll explore the impact of planetary gears throughout history. Now, as a group, we won't discuss each example in detail, but it's important to note that our journey begins in ancient Greece as far back as 500 BC. Fast forwarding several hundred years into the 13th and 17th century, we now have advances in clockmaking using planetary gears. And then it's further capitalized on during the Industrial Revolution with the integration of gearing systems for steam engines. We will do a deep dive into Babbage's difference engine. And then finally talk last about a technology used today in common automotive transmissions. Ancient Greeks. Historical records indicate that ancient Greek civilization, again, starting approximately 500 BC, invented and developed the principle of epicycles. Now, epicycles are systems of circular gears designed to travel in precision-based circular orbits. The Antikythera mechanism, circa 80 BC, was an ancient Greek hand-powered model of the solar system. It was comprised of several epicycle gearing systems built closely to match the moon's elliptical path. In fact, the epicycle mechanism was so advanced, it was designed to correct for a 9-year precession, which is a slow change in the moon's rotational orbit, astronomical position, and eclipses decades in advance of the actual occurrence. This ancient invention is the oldest known example of an analog computer. The Renaissance era. During the early 14th century, mechanical clocks were comprised of sophisticated gear trains necessary for precise timekeeping. Using principles of epicyclic gearing, Henry de Vic designed and built an all-mechanical clock in 1360, which established fundamental clock making design for the next 300 years. This occurrence signified an elemental shift for measuring time by continuous processes, such as the flow of liquid in water clocks, to a repetitive oscillatory process that provided a more accurate approach to timekeeping. Now, the Babbage difference engine, developed in 1822. The use of various gearing systems, not exclusively, but including concepts related to epicyclic gearing in Charles Babbage's mechanical computer, the difference engine, demonstrated how gears could be used to perform automated mathematical calculations, making it one of the earliest steps towards modern-day computing. Babbage's difference engine demonstrated how mechanical motion could perform automated calculations, marking an early milestone in both precision gear engineering and the evolution of computing technology. In fact, the difference engine could compute polynomial functions using the method of finite differences, perform equations such as additions and carryover operations automatically, and generate accurate mathematical tables, helping to eliminate many of the human calculation errors common at that time in printed navigation, engineering, and astronomical tables. This technological advancement was significant at the time because it showed that mechanical systems, thanks to gearing, could process information, not just transmit power. Modern day applications of planetary gear systems. So here are a few examples. So planetary gears in wind turbines convert or boost slow rotor torque, i.e. 10 to 60 RPM, into high speed, 1,000 plus RPM operation for power generation. In automotive and marine transmissions, they provide multiple gear ratios in a compact space, ensuring smooth shifting and effective torque handling. Robotics. In robotics, planetary gear systems are essential because they combine high torque output within small form factors used, for example, in manufacturing and surgical robotic arms. These gears allow joints to move with precision and strength while keeping the overall design compact and lightweight. Without planetary gear sets, many of the smooth, accurate, and repeatable motions inherent to robotics would not be possible. So here's a question for the group, and we can use the chat to answer. But can you identify one key reason why gears matter? Give it a few moments here. So our second agenda item, planetary gear fundamentals. So what exactly is a planetary or an epicyclic gearing system? So thus far, we've discussed equipment applications, but let's take the next few minutes to review the specific parts and components of a planetary gear system. Before we do that, to ensure we're aligned as a group, we'll take a few minutes to review basic gear terminology. Okay, we won't go over them all. We'll just focus primarily in on the first four. For the first four, the first one being input speed. So input speed is defined as the rotational speed delivered from, in our examples moving forward, AC electrical motors, measured in revolutions per minute or RPMs. The output speed is the rotational speed post gear set or gearbox delivered to the driven equipment after the gear reduction process, also measured in RPM. The gear ratio is the ratio between the rotational speed of the input and the rotational speed of the output gear or gear set. It determines how much speed is reduced by and provides an indication regarding the torque increase. For example, a 5-to-1 ratio means that the output shaft rotates once for every 5 rotations of the input shaft. And for our fourth key terminology here is torque. Torque is the rotational force produced by the motor and transmitted through the gear system, measured in pounds-foot or Newton meters. As speed decreases through gearing, torque increases. The components of planetary gear mechanism. First and foremost, the sun gear. So the sun gear is the central gear of the gearing system. It's driven by an external power source, i.e. a motor or servo, and its rotation drives the planet gears. The planet gears are the gears that orbit the sun gear. They're meshed with both the sun gear and the ring gear, creating the gear train. It's important to note that a unique feature of planetary gears is that they share the torque load equally. Third, the carrier. Carrier is the component that supports the planet gears and is connected to the output shaft via the gear train system. And then finally, the ring gear. The ring gear is the outer gear of the planetary gear system. It's affixed to a stationary frame in our case and provides support for the planet gears. So different type of gearing configurations and arrangements. So for this particular example, we're looking at a single stage planetary gearbox. This is a complete gear set: sun, planet, ring, and carrier. And some of the characteristics is the simple fact that it's extremely compact based on the reduction ratio that we're able to achieve with it. The efficiencies range for single stage gearbox to approximately 97%, but there are limitations. The gear reduction ratio for a single stage generally begins at 3-to-1 and is limited to a maximum of approximately 10 or 11-to-1. Achieving higher ratios in a single stage will require a very small sun gear relative to the ring gear, which could lead to issues with tooth strength and the number of planets that can actually physically fit within the gearbox itself. Here's an example of a multi-stage planetary gearbox. So when higher reduction ratios are required or specific output speed is needed that a single stage cannot provide efficiently, then we would in turn rely on a multi-stage configuration. So the total gear ratio in this specific project is the combination of both planetary gear ratios. In other words, for example, a 2-stage gearbox with a 5-to-1 ratio in the first stage and a 4-to-1 ratio in the second stage will yield an overall ratio of 20-to-1. Some of the key characteristics here, so we can achieve very high gear ratios from 15-to-1 to several hundred to several thousands, as we discussed earlier, for power generation and wind turbine uses. It does, however, we need to be mindful, increase the overall length due to the number of planetary gear stages that we put in series to the gearbox. And then finally, we need to take into account the slight reduction in efficiency. While each stage is highly efficiency, there is a small loss associated with each additional stage. However, for two-stage gearboxes, we normally maintain an efficiency rate between 90 to 95%. Here is a comparison chart, which outlines the differences between the structure, the reduction ratios, the sizing, efficiency, complexity, and so forth. And again, something to just be mindful of are the limitations for single-stage planetary gearbox of 11-to-1, and then the need to increase the staging when we need to achieve output speeds that require a 15-to-1 and higher gear ratio. Here are the side-by-side comparison. So we visually now know how much larger a multi-stage is versus a single stage. Now we're going to resolve one of the questions is, okay, planetary gears in water management, where they commonly used specifically as it relates to submersible mixers. So submersible mixing equipment is used to reduce speed. We know that, to increase torque. And they utilize planetary gear systems across the water and wastewater industry. They are especially valuable whenever equipment must move large volumes of fluid or solids at controlled low speeds. Feel free to take a screenshot. We won't delve into these extensively, but these are just simply some examples of planetary gears in submersible mixers throughout the wastewater treatment process. Question for the group, and we'll answer this via the chat. Can you identify the 4 components of a planetary gear system? We'll give it a few moments here. Now, the planetary gear mechanics. So here is a gearing system in action. Switch over to the laser pointer. Starting from the left, we have the motor input, and that shaft is connected to the shaft for the sun gear. The sun gear, again, as we learned earlier, is responsible for the directional rotation of the equipment, and the planetary gears hence are orbiting around, moving around the sun gear, and are held in place by the ring gear. Now, one observation to note is the gearing ratio. So here we have a particular speed input, and then our output, due to the gearing system, is significantly reduced. Gear ratio, a brief recap, describes how rotational speed and torque change between 1, the motor input, and 2, the output, i.e. the driven equipment. Why gear ratios specifically matter with submersible mixer. So thus far, we know the following. Gear ratio determines the relationship between the speed, in our case, specific to the mixers, and the propeller performance. And that's important for several different reasons. The first one being the propeller speed. Proper mixer propeller speed ensures stable laminar flow patterns. It also prevents excessive turbulence and improves overall mixing uniformity. Number 2, the torque output. Wastewater often contains sludge organic solids, fibrous materials, and highly viscous fluids. Higher gear ratios increase torque that allow mixer blades to operate in heavier fluids, all the while maintaining the correct solids suspension rate. And then third, the energy efficiency and motor sizing consideration. Finally, gear ratios matter because they directly contribute to energy efficiency efforts by delivering optimum fluid movement per kilowatt consumed, consequently minimizing wasted energy by correctly sizing the motor itself. We'll review several examples shortly, highlighting the various points pertaining to one, motor and propeller speed. So first, let's talk about the gear ratio impact on speed of the equipment itself. Here is the formula for gear ratio with a fixed ring configuration. So in order for us to know what the actual ratio for this specific gear train, we have to take the number of teeth on the ring gear and then divide them by the number of teeth on the sun gear. For example, the ring gear with 48 teeth, the sun gear with 12. We plug in our formula. 48 divided by 12 is 4, plus 1 gives us a 5-to-1 gear ratio. Now that we know our gear ratio, and we could safely estimate our motor speed by the nameplate information, we now need to determine, okay, so what does that mean as far as our output speed? In other words, in our case, again, for submersible mixers, our propeller speed. So a lower gear ratio yields a higher output speed. And in this case, we have a 4-pole motor spinning at 1750 RPM and a gear ratio of 10-to-1. Our output speed for this case now is 175 RPM. So if a lower gear ratio nets a higher output speed, it's fair to say that the inverse is true. In other words, if a higher gear ratio would then net a lower output speed. And if we're using the exact same speed motor, but with a higher gear ratio, we plug in the numbers, our output speed equals motor speed divided by our gear ratio, which nets an RPM of 87.5. So when do we need high or low speed outputs for wastewater, specifically in mixers again? High intensity mixers typically require higher RPM. We need to achieve that agitation. As we're blending fluids, our RPM demand begins to diminish. Our ratio for gearing increases. Now we have sludge mixing, which requires a much lower or moderate RPM. And then for flow induction or large blade mixing, moving fluids from point A to point B, specifically in oxidation ditches, we require low RPM output from our machines. So that's the speed. Another formula here and a question for the group. So if we have a ring gear at 80 teeth and a fixed teeth setting of 30 for the sun gear, we know through Wilson's equation that we need to calculate these by gear ratio equals plus 1 in the division from 80 to 30. We'll give a few moments for the group. Calculate that. And if you would, go ahead and put your answers in the chat. Moving along. 1 plus 80 divided by 30 yields a gear ratio of 3.66 by 1. So the output gears revolving once for every 3.6 turns of the input gear. So what is the gear ratio's impact on torque? And why planetary gears produce high torque? So one of the most compelling advantages of PSG's planetary gear system is the exceptional torque density. This refers to their ability to transmit very high amounts of torque relative to their physical size and weight. But how is this achieved? Some of the benefits here is through load sharing. The primary reason for this high torque density is the distribution of the load amongst multiple planet gears. In a conventional parallel shaft gearbox, we reviewed that earlier, the entire load is transmitted through a single mesh point between a driver and a driven gear. In contrast, in planetary gear systems, the torque is shared amongst several planet gears, 3 or 4 respectively, effectively multiplying the contact area transmitting the power. Second point is stress distribution. This load sharing means that each individual gear tooth experiences less stress compared to a single mesh system handling the same torque. This allows for smaller gears to transmit greater power or for larger gears to transmit significantly higher power without increasing their physical dimension proportionally. And then finally, the compact power. This inherent design characteristics makes planetary gearbox ideal for applications where space is limited, but high power transmission is required. All right. So we answered the how. Now we'll talk about when higher torque is needed. So we'll first attempt to resolve the where. So where is higher torque needed when mixing? Very first application would be somewhere where a client is experiencing a high solids content. This could either be in an influent pump station or a pump station prone to heavy fog, fats, oils, and grease buildup. The second is if we're trying to mix heavy viscous fluids. So this could be, in some cases, some mixed liquor applications. Third one being dense sludge, so a sludge holding or tank or a septic receiving tank. And then finally, large tank volumes. So in our case, oxidation ditches. Now let's resolve the why higher torque is needed. First, the first order of business is to assist in preventing solid settling. Dead zones or areas within basins or tanks that accumulate debris are less than ideal for the operation of the plant. Secondly, we get to experience the maintenance and suspension of solids. And then lastly, the reduction, or at least the attempt to reduce the excessive clogging or ragging experienced by some equipment. All right. So determine the torque in a planetary gear system. So in order for us to determine what the output torque is, first we need to calculate the input torque. Once that's defined, we would then multiply that by the gear ratio times the efficiency, and that will then give us our output torque for the equipment. So in this case, measured in pounds-foot, we have a constant here, 5252 times horsepower divided by RPM for the input torque. In our example, we have a 10 horsepower motor operating again at 1750 with an efficiency rating of 96% and a gear ratio of 25:1. So in the chat, would this be a single stage planetary or a multi-stage planetary arrangement. Again, gear ratio equaling 25:1. So our input torque per the formula here is 30 foot-pounds. We've taken our constant times our 10 horsepower and divided that by our RPMs, giving us a net result of 30 pounds-foot. Plugging in 30 pounds-foot to determine our output torque, 30 pounds-foot times 25, our gear ratio, times the efficiency of the mixer gives us an output of 720 pounds-foot. So what's being delivered in torque. Okay, so where would, typical torque ranges in wastewater mixers? Starting with the very highest first, we talked about digester mixing and making certain, given the thick nature of the materials, that it's being mixed properly. The mixture would need to perform at a very high torque level. Thick sludge, again, high torque demands needed, but not as much as within a digester. Activated sludge, waste and or return activated sludge would need moderate torque. And then finally, lower solids mixing is at the bottom of our scale here. So our key takeaway is that higher solids concentration net higher torque requirements. Question again for the group. This is a softball, an easy one for everyone. Does torque increase or decrease as the gear ratio increases? Does torque increase or decrease as the gear ratio increases? Now, our last point in the agenda for today, energy efficiency in submersible mixers. Tina mentioned this very early on in the introduction, but according to various studies throughout our industry, due to their quantities, in other words, typically you have 1 to 2 mixers per tank or 2 to 3 mixers per basin, and the 24/7 operation required, submersible mixing equipment can rank as high as the second largest consumer of energy and power in the wastewater treatment process. Hence, our goal or primary benefit would be for our clients is to reduce the operating costs. How do we get the most efficient mixing equipment available and reduce the owner costs, both in power, maintenance, and support any sustainable goals that they may have? So if grant money is involved, so forth and so on. Key factors impacting submersible mixer efficiency, while factors such as motor operating speed, torque output, motor efficiency, and propeller blade design contribute to the overall mixer efficiency calculation. The largest influence that can be realized is through the gear ratio. Let's explore that statement in more depth. And we'll resolve this by attempting to resolve this question. So how mixers use energy, okay? So the primary objectives of submersible mixing system is severalfold, but it's really to maximize the fluid movement, i.e. the thrust, while minimizing the energy consumed. Effective mixing is achieved by generating the proper combination of speed and torque to maintain solid suspension, prevent settling, and to promote uniform process conditions throughout the tank or basins. Energy efficiency in mixing is not driven solely by the motor size or by the motor speed, but by optimizing the entirety of the system. This includes propeller design, hydraulic performance, operating conditions, but most importantly, as per the previous slide, the gear ratio. High thrust, low speed mixing is often more effective and efficient than high speed operation because it moves large volumes of fluid with reduced turbulence at a lower power demand. Our goal again here is to maximize fluid movement thrust while minimizing energy consumption. How planetary gear stages increase mixing efficiency. So what we're looking at here is an input to thrust performance chart. Okay, so power represented in kW is on the X or the horizontal axis, and thrust represented in newtons is on the y-axis. In this example, we're utilizing the same power input, okay? And I'll show you a little bit further what that means. But one observation that you can make is that for the green dots here, we have approximately at the different speeds, the power, and then the thrust tend to migrate towards the lower portion of the power to thrust chart. In other words, direct drive mixers produce the lowest thrust. Now, given what we know, we've now introduced, i.e., multiplying our thrust, slowing the mixer unit itself down with a one-stage planetary gear system. And that scatter chart is represented by the black dots here. And then third, we've got the planetary gear system. So the two-stage planetary gear system. And what exactly does it mean? So if we use, for example, a motor input with 3.5 kW. For a direct drive mixer, we average approximately 500 to 800 newtons of thrust, respectively. Now we're stepping the thrust output out with a one-stage configuration, same motor, but the thrust output now is averaging anywhere between 1,000 to 1,500 newtons. And then the third, same motor with an output thrust in a two-stage configuration of 2,000 to 3,500 plus newtons. So the key takeaway here is that mixers produce 2 to 4 times more thrust with the same power input by utilizing a planetary gear system. Well, Harold, couldn't we simply use a VFD to slow our mixers down? Yes, that's certainly an option. But on average, you have a couple of different reasons why we may want to consider one or the over the other. So on average, the VFD's efficiency is approximately 95 to 98%, meaning that after the losses in the equipment itself, we now have to internalize the losses with the VFD. And those losses are realized through several different means and through different ways, but through the switching, harmonics, and heat generation, and the cooling requirements, and an additional cabinet or control space that we would need to house this. The primary problem, however, is that planetary gears are purpose-built, and they increase torque mechanically, not electronically, and they allow the motor to run at or near its optimum speed or its best efficiency point. In addition to that, we can also increase the propeller diameter, as we saw in the previous scatter chart with the same input power, and you're unable to increase that propeller diameter on a standard direct drive mixer motor simply by overspeeding or utilizing a VFD. Here are some of the comparisons and some of the key takeaways as far as the type of speed reduction and the control methodology. But one area of focus we want to keep in mind, again, is the purpose-built reasoning behind the planetary gear versus another piece of equipment influencing speed and losing, for instance, the cooling capabilities and the torque output and reducing and minimizing ragging in wastewater applications. We won't go through all of the examples here, but just wanted to bring up several key takeaways for overall energy efficiency in submersible mixers. First one being that the motor operating at its BEP or best efficiency point is a net result of less wasted energy in the overall system. The increased torque, reducing required motor size, allows us to operate in mix with a lower power consumption, reduce heat generation. We're using work more effectively and efficiently with the same electrical inputs. So question for the group, and again, we can answer this in the chat. Identify a key factor in optimizing energy efficiency in submersible mixers. Hint, hint, this was pulled from the very previous slide, so feel free to drop your comments in the chat. So in conclusion, we'll go over our agenda items and just talk about how we finishing up our presentations here. But nonetheless, first order of business for us was to look at the historical impact, again, starting in ancient Greece and how we're realizing some of the technological advances over the last several centuries and using them today within the water management industry and space. Our second point was to look at and discuss the planetary gear fundamentals. So we identified the four components of the planetary gears and how they differ from other gear sets. So we have the sun, the planet, the carrier, and then the ring. And then our planetary gear mechanics, how gear ratios impacted, we discussed speed and torque output. And one thing we want to consistently keep in mind as it relates to planetary gear systems is that when speed is decreased, torque is increased. And we review the formulas that prove that out. And finally, how do we take everything we've learned over the last few times in the last few centuries and implement those into submersible mixing? So planetary gear systems optimizing efficiencies by converting motor power into useful mixer energy with minimal loss. So our key takeaway for today's presentation is how planetary gears convert power into useful work efficiently and deliver high torque needs and precise speed control in demanding water management systems. Again, my name is Harold Adams, National Sales Manager for the Water Management Segment Business of Wilo USA, and I greatly appreciate both your time and participation in today's Power in Motion presentation. Thank you.